Hey YouTube, it's Dimitri, and today we're going to talk about regression versus decision trees, when to use which model and why. So as it says here on this slide, don't throw mud. This is kind of the analogy of don't throw mud on the wall and hope it sticks. I say this all the time because I see so many people that are trained in data science, statistics as well now. For some reason, we're like going down this rabbit hole of kind of the data science approach of just throw as much stuff on the wall and let it stick. And if it sticks, we use it. If it doesn't stick, we don't use it. Real quants don't do that. Real professionals don't do that. But today we're going to go in the difference between regression and decision trees. So you don't have to try to build a whole bunch of random models and then just pick which one fits the best, which is what we see a lot of times. So let's just dive on in. For simplicity's sakes here, this video, we're only going to be discussing a univariate case here. So we're going to predict y with the variable called x. In the real world, these things get a little bit more complicated, but you can apply the same ideas because you could have like x and, you know, x1, x2, x3, x4, all the way out to xn, and you could have a full entire equation. Now, this applies both to linear regression and decision trees. So again, in a decision tree framework, this would be the equivalence of having like one variable and splitting it, and you can split it on a bunch of different sections, which we're going to see here in a second. Or, you know, you could just take one and split it in a few parts, like one split on its own. But in the real world, in decision trees, you should have, you know, a bunch of different variables, and you'd split, you know, based off of one variable, and maybe you split off of a different variable, and then maybe you split the original one into different parts based on that. Complexity's sake here, we're not doing multivariate, we're just going to do a univariate example here. Again, OLS is the simplest linear regression model possible, so I'm going to use that. We're not going to deviate into other types of linear regression, but we can assume here that, you know, y is what we're predicting is going to be equal to alpha plus beta x plus epsilon, where alpha is the intercept, beta is the coefficient, x is our univariate variable that we're kind of modeling with here, and then epsilon is going to be the error term. Decision trees are univariate as well. So as I mentioned, we're going to keep this consistent across the board so we can compare apples to apples. So linear regression, what are the pros here? Linear regression is continuous, meaning it is robust. The relationship itself is going to be linear. So things that are linear are going to be predicted well by linear regression. Yeah, no, who would have thought? But the cons here are going to be nonlinear relationships don't fit well. So there's an exception to this. We're going to get down into the details on here. Now, back to the robustness piece here. I think this is where a lot of people get stuck. And we'll talk about it a little bit with the decision trees here. But decision trees and a lot of machine learning techniques as well work really well within very defined frames of reference here. And so I see this a lot in the industry. People say, okay, Dimitri, I'm going to have a variable and I'm going to test, you know, like the stability of it, or I'm going to test the range of it because I want to see that it's not deviating too much. I want to make sure that, you know, it's stable. And so they ensure that it's stable. Well, of course, in machine learning, the issue here is that you don't have linear regression. So when we look back at this equation here, right, y equals alpha plus beta x plus epsilon, beta is that slope coefficient here. And that means x can take on any value from negative infinity to positive infinity, because the equation itself has a linear relationship, meaning that line has a specific slope. And that slope is what defines that line along with that alpha, which is an intercept term here. But essentially that line can predict any value for x that's negative infinity to infinity. You'll see here when we get into decision trees. So if you haven't watched videos on it, maybe I'll link something around here as well so you can understand better. But essentially a decision tree just takes an average value, so the mean of a specific group, that end branch, or that node there at the end there, the leaf as they call it. So it only will give you an average based on some sort of value. So if the model is built on a value, say from 0 to 100, and that's split up, that 100, you know, variable here is split up into like, you know, 0 to 10, 11 to 35, 36 to 82, 83 to 100, for example. Those are going to be the range of those values hold. It's going to take some sort of average here. Now, anything that is less than 0 or greater than 100 is going to have to get clustered with just a prediction inside that last leaf or node here. Now, the issue is when data in the real world, it moves and shakes, and it kind of shakes out of these parameters. Machine learning is considered brittle because it can't handle these sort of deviations in the input variables here. So it doesn't do very well in these scenarios. Now, there are many, many cases, which we're going to kind of hit on here, with decision trees where it works excellent, and that doesn't matter because we know for a fact our data is going to be bounded, or it's near impossible to go outside of these ranges. And in those sorts of cases here, decision trees are going to be great. Now, for decision trees, the pros here, so for regression, decision trees with regression, they do nonlinear relationships great, which we're going to see in a second here with a few examples. They do amazing also for clustered or step data here. So data that's going to be kind of grouped or clustered in different areas, and data that also has like step kind of functiony reality. Like, you have a cluster, say around like a Y value, so that thing we're trying to predict here, of like 10, and there's a bunch of them around there, and then all of a sudden it jumps and there's like a bunch at like 30, and there's a bunch like at 90. And often in science or in the real world, there'll be kind of groupings where it's like these things just happen in some sort of group, and then often there's not many in the middle here. This is called a step function. Anyways, it's a really good thing decision trees can pick up well. And finally, the con of a decision tree is going to be the lack of continuous prediction. So the robustness factor in decision trees is not great. This is one reason why you see people touting machine learning as like the fix-all solution. And then when you start to really dig deeper with them, you start finding out their model works great because they have to refit it all the time. So if you started having those deviations, on the upper end or the lower end, and more of them are getting added in, it's because they have to keep refitting that model constantly to keep it somewhat rejuvenated and to try to make it essentially artificially robust. Where linear regression here is just naturally robust. You don't need to refit and adjust. Now, again, you could refit and adjust if you wanted in linear regression as well, and you'd probably get a little bit better accuracy if you refit it more often, just simply because now you're kind of just cheating. You're not comparing apples to apples here. You can't refresh one and not refresh the other and then make the claim that, machine learning and decision trees in themselves fit extraordinarily well and are far better because you're not doing the same process here. And you can do that the same thing with traditional statistical models here with refits. So the first scenario here, you're going to really have 4 cases of, comparing what makes a decision tree in a linear regression different. Case 1 is going to be linear data. As I pointed out, linear data here, the blue dots, they fit extraordinarily well with this red line, which is going to be linear regression. So you can see from this far better approximation or fit here. And then you see these green lines. These green lines are the averages if I was to split this up with a decision tree, again, trying to capture these groups here. You can see, though, the model doesn't fit as well in the sense that a lot of the blue dots are going to deviate much further from the green lines that they have. So your error is going to be higher here in this scenario. Also, again, we lack robustness. So in statistics, we look at fit and robustness. So don't forget, you're trying to weigh the 2 pieces here and really make this work well. So linear regression does best on linear data. Okay, we all know that. Case 2 is linear data with clustering. So, again, it's linear data here. You can see these purple dots kind of go in a line, but they're clustered. We have like groupings of them. And when you do that here, linear regression doesn't perform very well. So this is kind of shocking to a lot of people that are gung-ho on the linear regression traditional stat side. This is a case where you can see, for example, depending on the different scenarios and data you have, these green lines actually look like they fit better here. Or maybe it's a mix, but realistically, there are many scenarios where you have linear data and you have some sort of decision tree that can model these clusters much more accurately. And this is a case where you'd want to use a decision tree if you can get better accuracy with this. Now, again, you'd want to look at the data and think about, like, is this data, going to deviate a lot in the future? And if so, you're going to have to refit a lot to keep up with it. Whereas linear regression is going to be more robust. So this is one of these gray areas where, a decision tree could be better, linear regression could be better, but you need to plot and look at your data and really understand what's going on here. The third scenario is going to be non-linear data. So this data has a curve to it. Again, you can see when you put a linear regression on here, we end up like fitting kind of the top part of this data. So anything greater than like 1,000, but if it's absolutely horrible on anything less than 1,000 because the data is curving down. And so that line can't fit it in linear regression here. Again, this is one of these gray cases on it depends how nonlinear the data is. So if you had like a crazy big S wave or something, linear regression might do absolutely terrible, where you might be able to use a decision tree broken up into enough leaves here that you would actually be able to get a really good fit with a decision tree. So again, case 3 is one of those gray areas on it depends how nonlinear this data is going to be. And then the fourth scenario is going to be non-linear data that is clustered. So this is like where decision trees shine here. So we saw case one, linearity, linear models win. The two middle cases here are going to be in the gray area. But case four is where you should see that, decision tree, like hands down, knocks out linear regression. And this is the best case scenario for a decision tree. So you see the linear line here, it fits terrible. It's trying to fit all this data that's clustered again in one area, and it's trying to get that linear relationship. And unfortunately, there are stragglers, it seems, that go way out on the right, and the errors with this model will be huge, meaning the model will not fit good. Now, again, linear regression will be robust, but as you can see, right, the robustness here essentially fails. So as robustness keeps going further and further out, due to the nonlinear nature of this data, the robustness is actually a bad thing in this case. It gets worse and worse and worse. Like the errors are getting absolutely terrible with this model. There's no way to use a linear regression in this case here. So at least based on the simple definition I've set up in this framework. You can see that the decision tree, even though it doesn't capture like between 0 and 1,000 extremely well, like it does worse than the linear line here. The linear line fits that much better in that little first case here, or I guess 0 to whatever that first decile kind of part is. The green line does okay, not great, but then in the remaining kind of two sections here, the other two lines for the nodes here, the other leaves for this decision tree, it does extremely well. So it's fitting great here. Again, I would use a decision tree in this scenario because one, robustness is not going to work here with the linear regression, and two, your fit's going to be much better with the decision tree. So this is the all-star case of when you would want to use a decision tree. Now, there's a sliding scale to the nonlinearity nature discussion here. So I've plotted all these data points. There's three different charts. The top left one is extremely nonlinear, and you can see it has a really good curve to it. If you put a line through there anyway, you're not going to get a good fit. But if you used a decision tree, you would get a stellar fit because it is extremely nonlinear. Now, if you go to the bottom left chart, we get like slight nonlinearity here. It's kind of in the gray area. Now, if you put a line on that, we probably could get some pretty good fit with the linear regression. And this data in this example doesn't have much clustering. So I'd actually use a linear regression model here because it would be more robust and actually have pretty good fit, where a decision tree would have to have too many leaves and get too complex, and it probably wouldn't predict well in the future. So again, we're starting to get in a gray area where it's like we might be able to use a decision tree and do well. We probably should use linear regression, right? But it's going to be a judgment call depending if your data is clustered or non-clustered, as we talked about. And then finally, this right chart here, again, it is still nonlinear, but linear regression is going to work well because that nonlinearity is quite small here, or more mathematically put, the convexity is low. So all of these actually can be modeled with a linear regression. So a lot of people, I don't know, don't think about this. The top left chart is x to the 6th power. The bottom left chart is x squared, and the one on the right is x to the 1.5, so it's a fraction. If you actually just plug that into a linear regression, you would get a line that would fit all of these extremely well. So yes, linear regressions, this is the exception I mentioned before. Linear regression can actually fit well if you just make the relationship nonlinear by using exponents. Okay, so technically that statement I just made was wrong. The relationship itself, the beta, will remain linear because it is linear regression. However, the variable x in itself will be a nonlinear transformation. So you can take that nonlinear variable and transform that into a linear kind of essentially relationship here, and then you can model that linear relationship with a linear regression structure. Now, this is not going to work if your data is not just like a nice pretty curve. If you have like an S curve or you have clustering pockets and the nonlinearity just like weaves all kinds of odd designs and patterns, you're not gonna be able to use a linear regression model to really capture those. There are ways around this. So we could do like Taylor series approximations and other sort of methodologies in linear regression. So linear regression is far more flexible as a framework than decision trees, but I don't think a lot of people know that because you just don't dig down that rabbit hole of all the complexities that they don't teach you in many classes, at least not at the base level. So regression, cases of when this should be used, when it's linear or near linear relationships, linear regression is going to be great at fit. It's going to be great at robustness. It's hard to kind of deviate from that. That's where it really shines. So linear regression is more robust, meaning the prediction coefficient domain from negative infinity to infinity it's just going to capture that full span, whereas a decision tree just can't do that. You have to keep redefining the relationships or adding more leaves to keep adding, more accurate predictions further out in different directions or kind of different stability areas inside of a variable, as data scientists like to call it. So linear regression is more robust in most scenarios here. We showed an exception to that as well. Exponential nonlinear relationships are a possibility. So as I mentioned, in these cases, you can take X and raise it to a power. You can also use Taylor series approximations and make cool designs and patterns, or you can use like sine, cosine, and capture wave patterns and whatnot. And also another point here is that clusters with overlapping range. So range is going to be the x-axis here that we looked at in some of these. When you start to have variables, so like in this chart here, you see the purple dots around like 25-ish. You start to have stacking, like the clusters are stacked. So you essentially have two y variables, like values here. So the top cluster on the 25 range is going to be somewhere around like, 40s. And then all of a sudden you have the same x variable here, but it's going to have y values around like 20. So when these clusters start to stack, in a univariate case, of course, it's hard to separate those because the reality is there's like two separate values for two separate y values for one x value. And so when you start using decision trees, you're gonna have to split a line like this through the middle of them. And you're gonna have two clusters that are above each other or below each other, stacked. And you're not gonna be able to capture that relationship because there's no way to split it to say, hey, the y values in these ones should be one, and the y values in the other one should be a different one. Now, again, if you had a multivariate case here, you could probably separate these out, and you could figure out like there's probably some sort of difference between these two clusters, and then you could add that variable in there to capture kind of that difference here. But if you're just having a simple case, be wary, just because you have clusters doesn't necessarily mean a decision tree is going to work well. Now, decision trees here, the great use cases for these are going to be clusters with minimal overlapping ranges here, as we talked about. So if you have clusters and pockets and they're all in different kind of weird areas on, this relationship here, you'll want to use a decision tree because it's going to do absolutely amazing at this. And this is where they really shine. Again, non-monotonic, non-linear relationships, things that are complex, things that just have really odd shapes and relationships. So like, for example, if you think about like a rainbow shape, linear regression is never going to be able to capture that very well, at least in the simple terms. And then a decision tree, though, could actually end up kind of capturing different sloped areas of that curve. You might be able to fit it fairly well. And then finally, logically bounded domain. So like probabilities do extremely well with decision trees because, right, it has to be between 0 and 1. There's no way outside of that. And in these sort of cases where your robustness in the sense of like the different domain of these values don't matter as much, it doesn't really, like, there's no added value by using a linear regression approach here because you don't really need that extendable robustness. And in this case, a decision tree would actually be a good thing to kind of consider here. So if you start looking at data and there's a logical boundaries on your data sets, I would start considering decision trees as a good alternative or even the dominant kind of approach to take here when modeling. And then finally, I wanted to talk about segmentation because I feel like many academic institutions and textbooks don't talk about this very much. But in finance, quantitative finance here as a whole, we use this a lot, especially in the credit risk modeling framework here. So if you look at this data here, we have a scatter plot of a bunch of just black dots. This is our data here. And you would say, okay, we're going to use linear regression and it's going to fit okay here. But, it's got some spread and whatnot. And the reality is if you understand the business or you start to do segmentation analysis and you look at different ways to segment your data, you'll find out here there's actually two kind of things going on here. So in this example, right, it looks like for some reason the data is kind of split. So all the upper values here are going to be kind of this, orangey pinky color. And then below that's going to be teal dots. You can see there's clearly a separation here. So there's two segments. You could actually use two linear regression models to predict this. And this is what we do in credit risk here in finance. Now, again, also, if you had something that looked kind of like like a pyramid or it went up and then it went down and you had some sort of way to distinguish between these two, you could actually have two separate regressions. Again, if you had clusters, as we mentioned before, that are stacked like these purple dots, you could actually, if there was some sort of other variable here. So as I mentioned, decision trees, right? If you had another variable, you could add into here. It's kind of like segmenting these out into other segments. But importantly, I think linear regression, you can also segment by just creating separate models. So In this case here, you might have a linear regression that covers like these top purple cluster, and you'd have a second linear regression that covers the bottom ones. But again, you need a variable to determine that segmentation. And the same thing can be done here with decision trees. When you start to add multiple variables into these models, you can actually create separate groupings here. But in linear regression, you could use the same variable and the same relationship. But if there's a third variable here, or I guess technically a second variable here, you could segment these out by that second variable, and then you could do a regression between your y and your x's. And basically, it would be like the same relationships, but on just two separate groups here. So I hope the takeaway here, the simple conclusion is linear regression does great on linear data. It does great on somewhat nonlinear data as long as you can figure out the relationship of how it's nonlinear. Linear regression is very robust, but linear regression does not work well on nonlinear relationships and issues with clustering in the data. Decision trees do exceptionally well on nonlinear relationships. They also do great for different sets of cluster data and step data functions here as well, but they just lack the robustness here in the prediction range. And so a little bit of caution needs to be applied when looking at decision trees. So I hope when you guys go to model in the future, you stop, you look at your data, you think about how it's, related to these kind of relationships with other variables, and you realize, my data looks to have a lot of clusters, or it looks quite simple and linear, or, I need to have an infinite range and quite robust for this model to work well. Or maybe it has a nice, pretty bounded structure here, and that will help guide you in selecting the correct model structure. So anyways, thanks for listening. Thanks for watching. And as always, until next time.